You think you've got atoms all figured out from those old school diagrams of the tiny nucleus in the middle like a sun. Electrons whirling around like planets in tidy orbits. It's the kind of image that's plastered in every textbook, hanging in science museums, and even popping up in cartoons. But hold on, because I'm about to shatter that illusion. That picture isn't just a simplification, it's dead wrong. Completely, utterly, and fundamentally off base. It's the kind of wrong that makes you wonder what else they got backward in class. If you stick with me, I'll take you on a journey into the real heart of the atom where things get so bizarre. So, against everything your everyday senses tell you, that your mind might rebel, but trust me, it's worth it. This is the stuff that powers the universe. And if you're not subscribed yet, do it now so you can catch more reality-bending science like this. Let's jump in. To really understand why that solar system model is a myth, we have to go back to how we got here. The idea of atoms dates way back to ancient times. In the 5th century BC, Greek philosophers like Leucippus and Democritus proposed that everything is made of tiny, indivisible particles they called atomos, meaning they imagined these as solid, eternal bits of matter bouncing around in empty space. It was a brilliant guess, but they had no experiments to back it up. Fast forward to the 19th century, when chemistry started getting serious, John Dalton, an English scientist, revived the atomic idea in 1808 with his atomic theory. He said atoms are solid spheres. Each element has its own kind, and they combine in simple ratios to make compounds. This explained laws like conservation of mass and multiple proportions. Dalton's atoms were like billiard balls hard, massive, and unchanging. But cracks appeared soon. In 1897, J.J. Thomson discovered the electron using cathode ray tubes. He showed these rays were streams of negatively charged particles much lighter than atoms. This led to the plum pudding model. The atom as a positive sphere with electrons stuck in it like raisins in pudding. It was the first hint that atoms had internal structure. Then in 1911, Ernest Rutherford, Hans Eger, and Ernest Marsden did the famous gold foil experiment. They fired alpha particles, helium nuclei from radioactive sources at ultra-thin gold foil. Most particles went straight through, but a few bounced back at sharp angles. Rutherford was stunned, saying it was as incredible as if you defired a 15-inch artillery shell at a piece of tissue paper and it came back to hit you. This proved the atom is mostly empty space with a tiny, dense, positive nucleus at the center. Electrons must be somewhere around it. But how? That's where Niels Bohr came in 1930. A Danish physicist, Bohr was trying to explain why hot gases emit light at specific wavelengths, not a continuous rainbow. He proposed that electrons orbit the nucleus in fixed circular paths, like planets around the sun. But to fix the stability problem, classical physics said orbiting charges should radiate energy and spiral in. Bohr added a quantum twist. Electrons can only occupy certain orbits where their angular momentum is L equals nk, where n is an integer and k is reduced Planck's constant. When electrons jump between orbits, they absorb or emit photons with energy equal to the difference, E equals hf, from Planck and Einstein's work. This matched hydrogen spectrum perfectly. The Balmer series in visible light, Lyman and UV, Pouchon and IR Bohr's model was a triumph, earning him a Nobel in 1922. But it was ad hoc. It worked for hydrogen, but failed for helium and beyond, and it didn't explain why quantization happened. The true breakthrough was quantum mechanics in the mid-1920s. It started with Max Planck in 1900, who introduced quanta to solve the black-body radiation problem. But it exploded with Albert Einstein's 1905 photoelectric effect paper showing light as particles, photons. Then Louis de Broglie in 1924 hypothesized that matter has wave properties, equals hp. Werner Heisenberg developed matrix mechanics in 1925, introducing uncertainty. Erwin Schrödinger created wave mechanics in 1926 with his famous equation. Paul Dirac unified it with relativity in 1928, predicting antimatter. This new physics showed the atom isn't a miniature machine. It's a realm of probabilities, waves, and the old models were classical approximations, but reality is quantum. So, with that history in mind, let's dissect the atom for real, starting with hydrogen. Hydrogen is the simplest. One proton, one electron. The proton is in the nucleus, about 0.877 fm, 1015 m across recent measurements from Wannick Hydrogen refine this. The electron is around it, with the average distance, the Bohr radiusa underscore O equals 5.29 times 10^11 m. But asking where is the electron right now is the wrong question. In quantum mechanics, the electron doesn't have a precise position until observed. This isn't due to clumsy instruments, it's fundamental. The electron is in a superposition of positions. Superposition means the state is a linear combination of possibilities. For example, in math terms, if left greater than and right greater than are states, the actual state is left, right greater than where 2 is 2 equals 1 are probabilities. When measured, it collapses to one or the other with those odds. Experiments confirm this over and over. The electron double-slit experiment is classic. In 1927, Clinton Davison and Lester Germer at Bell Labs showed electrons diffracting off nickel crystals, proving way of nature, Nobel in 1937. In 1961, Claus Jensen did it with slits. In 1989, Akira Tonomura at Hitachi sent electrons one by one each hits as a particle. But the pattern builds to interference. If you try to watch which slit, say with light, the pattern disappears because the measurement disturbs the system. This has been done with atoms, molecules like C60 fullerenes in 1999 by Marcus Arndt's group, even with 2000 data molecules in 2013. It's universal. The wave function encodes this. For hydrogen, the time-independent Schrödinger equation is 2/2 of a meter. 2 V, with V equals E, A4, 0, E. Solutions RE NLM equals R underscore NLRY underscore LM radial function times spherical harmonics. Probability to DV foreground state 1 south, UME underscore 3, ERA underscore 0. Probability peaks at R equals 0. But 4ag elevado cuadrado 2 peaks at A underscore 0. The electron isn't spread like butter. It's point-like upon detection, but the wave is the full description before. People often misthink the cloud as the electron smeared. No, it's probability. Like in crime shows, heat maps show where a fugitive might be, but he's at one spot. But in quantum, there's no hidden spot. The wave is reality. Richard Feynman said, "Things on a very small scale behave like nothing that you have any direct experience about." Now, why no orbits? Classical electromagnetism says accelerating charges radiate. James Clerk Maxwell's equations in 1865 describe this. For circular motion, centripetal acceleration A equals VAR, Larmor power P equals 0K elevado ao quadrado elevado ao quadrado 6. For electron, V tilde C, 137 fine structure, constant age, A underscore 0, calculation, time to collapse tilde 1011s. Joseph Lermer derived this in 1897, but atoms are stable hydrogen in ground state, doesn't radiate. Quantum states are stationary. The expectation value of current is 0. No classical radiation. If not, orbiting, maybe stationary. No Heisenberg uncertainty. X P2 e X. A 0. P 2A0. V 2 metros A 0,10 elevado a 6m SI. So, inherent fuzziness. Heisenberg formulated this in 1932. It's not measurement error. It's nature. If you squeeze position, momentum spreads. So, the electron exists as its wave function. Orbitals are those allowed states. Orbital from orbit, but it's misleading. It's a spatial distribution. S orbitals, spherical. P, dumbbell. D, clover. F, more complex. Shapes from angular momentum, quantum number L equals 0 to 1. 4L equals 1M equals 101. P underscore X, P underscore Y, P underscore Z as linear combinations. Higher energies for N equals 2. E equals minus 13.64 equals minus 34 eV. Shapes to south sphere with node, 2 P dumbbells. The weird part, transitions are quantum jumps. New smooth path. In 1913, Bohr postulated it, but quantum mechanics shows the wave function changes discretely upon interaction. How? The math says, so timed appendant perturbation theory for absorption. Experiments like atomic clocks use this precision. The electron is a quantum object, particle in accelerator tracks in cloud chambers, wave in interference. No classical analogy. Feynman, do not keep saying to yourself, if you can possibly avoid it. But how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Measurement wave function evolves unitarily via Schrödinger, but measurement projects onto the problem. What's a measurement? Von Neumann chain system plus apparatus plus observer. Copenhagen collapse at observation. It's unsolved, bothering physicists since 1920s. Interpretations, many worlds, Everett, 1957. All branches exist. Why? From relativistic QFT spin statistics theorem Pauli 1940. But why the theorem deep symmetry? Solidity, Pauli makes electrons resist overlap plus M repulsion. You don't fall through floor because electron clouds repel. Nucleus protons positive, neutrons neutral, but protons repel, so strong force binds. Yukawa predicted pions in 1935, found 1947 but deeper. Quarks Joman Zweig mu 1964. Proton Uday charges two-thirds, Minizun Teiksu, neutron Uji, colors red, green, blue, neutral combination. Gluons exchange color, 8 types, QCD, strong coupling at low energy, confinement, weak at high, asymptotic freedom, gross polar, Vilcek Nobel 2004. Quarks don't sit. They're in sea of virtual gluons quarks, proton mass 9038 MeV, but up-down quarks approximately 2 to 5 MeV. 99% from energy E equals mK. Lattice QCD simulations confirm nuclei. Binding energy per nucleon peaks at iron 56, while stars fuse up to iron. Overall, atoms are field excitations. QFT, fields, fundamental particles, quanta, electron field, Dirac, photon, M field, standard model, 6 quarks, Say's leptons, gauge bosons, Higgs, vacuum, Dirac C, but QFT vacuum has 0-point energy. Virtual pairs pop, pair uncertainty, E, TK2, Casimir effect, plates closer than wavelengths suppress modes, attract, measured 1948, precise now. Empty space in atom, no fields fill it. Empty is 99.999999999999996% by volume, but fields active, touching M fields repel at 0.1 nanometer. Size, electron radius Y minus 22 M from LHC. Point in SM, but strings suggest 10, 35 M spin. Intrinsic, like tops, but not. Stern-Gerlach, 1922. Silver atoms, unpaired electron. Split inhomogeneous field, quantized energy quantization, wave function boundary must be seen. Integer wavelengths. Spectra precision, G factor 2.0, 0231 930 436 182. QED predicts 212 digits. Probing, Compton, scattering 1923, wavelength shift. STM, 1981, images, atoms, via tunnel. Quantum in life, photosynthesis, quantum walks, efficient, magnetoreception in birds via radical pairs spin, tech, LEDs quantum wells, solar cells, excitons, quantum dots, philosophy. Does wave function represent knowledge or reality? Psi-epistemic versus ontics. PBR theorem 2012 favors on future, beyond SM, dark matter, gravity. In conclusion, the atom is Mathelbert space vectors, operators, beautiful, strange. If mind blown, like, comment, surprises,